realize that. Okay, now it's fixed. Sorry, I had the wrong thing selected. All right, so a couple of reminders. So we do have our field trip on Tuesday. So again, no class. And then I talked about the alternative assignments. I'll probably make an announcement about that. I've just been a little behind on everything. Sorry, I was trying to change my mapping too. All right, there we go. Too many computers. And then we still have our lab today, so we're doing our one-pot reactions. And then next week will be makeups for lab. And of course, you can always squeeze them in again on the day that you don't have lab, but if you have a lot to do or if you've been saving them, again, next week, Thursday, is a good time for that. Other questions, comments? Just kind of barreling our way through the quarter. All right, so where did we leave off on? Oh, I think we skipped. And so we just wanted to finish up this part. So predicting whether our metal will dissolve in acid. And so again, you guys got a taste for this in the activity series. And so you tested that. So your metal's dissolving in acid. So like we saw, if our reduction of H plus is easier than our reduction of our metals. So let's go back to our activity series for that one. So there's H plus. And so let's see, so what should have dissolved? So hopefully all of these metals, and then copper does not dissolve, for instance. And then most metals dissolve in nitric acid. And then you have this special combination, and I think it was part of your reading question slash, it's also just a fun fact. So part of, I think you remember from your book, I forget now who it was that won the Nobel Prize, but he basically had a gold piece of metal and then hid it right from the Nazis by dissolving it in a mixture of nitric acid and hydrochloric acid. And so this is called aqua regia. And so it's generally, if I remember correctly, a 3-to-1 ratio of HCl to nitric acid. And then just kind of fun facts slash safety tips. So you generally don't want to be storing aqua regia solutions. They could tend to be unstable. I was kind of curious how long he kept this solution around, or maybe it just doesn't do much if you have gold in this mixture. Because I do have a story about aqua regia and why you're not supposed to store it. And so this didn't happen to me, but it happened to another person in grad school. And they were just happily at the fume hood doing their thing when there was an explosion underneath them. Luckily, they were fine. But what had happened is somebody was attempting to store some aqua regia solution. Sometimes it's used to clean primarily what's it's called a frit. So instead of using our Buchner funnels with the paper, you have these filter frits that are quite wonderful, except they're a pain to clean. And you can't clean them with bases because bases will dissolve that. And so sometimes chemists use aqua regia, but again, it could be potentially explosive if they're organics or something around in there. So don't try to store it. You have to make it fresh, use it, quench it. At least that's generally how I've handled it before in the past there. So it's kind of fun fact. So that's how you get, again, those gold or platinum complexes to dissolve. And so that's part of the tricky part of the synthesis of some of these molecules. I think I've kind of hinted that you can make gold and platinum compounds, and sometimes it's to use them in your research. And so I have personally witnessed somebody dissolve some gold to then make a gold precursor to then go stick in research, which it's a little painful to watch somebody dissolve that nice little gold bar. All right. So now let's get to our math part that we've all been waiting for. So now connecting all of these. So our cell potential to then, of course, our Gibbs free energy and seeing how that relates to our equilibrium. And again, just kind of a recap, putting everything together. So we've established that our spontaneous direction proceeding in the forward direction will then have our negative delta G. So kind of star that if you need to. And then like we've seen now, okay, well, it's got to have a positive cell potential. So again, that's what's driving the electrons forward. So kind of like the waterfall is maybe the mental visual of that. And then looking at our K, so right, if we have a K that's greater than 1, okay, saying that our equilibrium, again, lies towards the products there. So then we kind of have our little relationship, how to go from G to our E cell to K. So that's kind of convenient there. And then let's keep looking. And so looking at how we go from our delta G to our E cell or back and forth. So we have this equation. And so this is where we take into account the number of moles of electrons so involved in that process. So we'll do some examples together. So we do need to keep track of our electrons now. So remember, right, the E cell, we didn't have to scale it, but when we do our delta G, doing that equation, we do need to account for that. And then, so our formula, negative delta G equals negative NFE. So, right, our E cell that we find in volts, so that's fine. And then we need to plug in to that Faraday's constant, which is this 96,485 coulombs per moles of electrons. And then we'll also look at this formula. So it's written up here. And so I believe that it is correct in this form. And then I'll point out there's a small typo in the lecture notes later on when we see this. But this is correct here with the 0.0592 volts over N times the log of K. So it should be log with the 0.05. So again, I'll point out the error in my notes. But I believe your book has it all correct in there. All right, so now let's just try this one. And so now let's just calculate our delta G, except now we'll use our E cell potential. That is one thing I haven't printed. So hopefully you have a table or maybe your textbook. If not, that might be something I need to eventually print out. But let's first figure out, right, our E cell potential. And then from there, can you go ahead and plug it in to this delta G? And so again, I'll probably rewrite the reaction. So delta G equals negative NF E cell. And again, this E cell is just kind of our standard cell potential. So we'll start to get into a little bit of the different conditions. So go ahead and try that. If I need to flip to the other page of cell potentials, let me know. You can probably also ask the internet for half reaction potentials. Let's see, online's reporting some issues with the cell potentials. So I don't know if they're in the book or not. So let's see, I'm trying to find iodine on here. So I believe that's our iodine cell potential. The book doesn't have it. Again, you can always just kind of Google any table of standard reduction potentials. And again, right, there could be minor discrepancies in the voltage, but so there's our value for iodine. And then I believe bromine's up here. So I'll let you guys copy that. And then if I need to flip back to the problem, just let me know. So how's our problem going? Did we at least figure out our cell potential? I'm going to sketch out that first here. So just rewriting our reaction. So our two half reactions. And so it looks like the chat has it. Let's just flip back. So we got bromine, so then we have to flip that. So negative 1.09 volts for that process. And then iodine to iodide. So again, flipping back. So we can leave that, so 0.54. And add those numbers together, which, so chat got negative 0.55 volts, which I believe will be correct once I pull up my calculator. And then from there, right, again, all you have to do is plug this in to our G. Sorry, I'm slow in finding my calculator. All right, so I finally caught up to y'all. So negative 0.55 volts. And then let's go ahead and plug this all in together. So delta G, just rewriting it again, equals negative F E cell. Again, that's standard E cell. And so now this is where we want to take into account our 2 electrons. So it was a 2 electron process, right? And so now we can put our -2 here times, so Faraday's constant, 96,485 coulombs per mole, and then times our -0.55 volts. And so you can already see that that's going to give us a positive delta G, which again, we were expecting from this negative number. And then let's just quantify that. And so I get, well, let's put this in. So this is in joules, so let's put it in kilojoules for my own sanity. So about delta G is positive 106 kilojoules roughly. And looks like chat got the same. Then did we get that in here? So let's try that again just for practice here. And so now let's do this reaction. Oops, lost my arrow. And so now we're looking at, well, I'm predicting it's going to be a spontaneous reaction, right, just from what we know. So the reaction of sodium metal plus water to give us H2 gas and hydroxide, and of course, sodium ions. So see if you can repeat that process. Again, unless there are questions on here, but I think it went smoothly. So find your cell potentials again. So calculate, right, E cell, and then delta G from that. And I can also flip back. So I'll give you all a second to kind of write your equation down. I'll flip over here for a second. So where's sodium metals? Probably down here. So there's sodium. We have to find our water one. There we go. Finally found the water one. Scrolling around like crazy. Then if I need to flip back, I can. So I'm just kind of sketching out our cell potential again. So it should be positive 2.71 for this direction. And then we have to find, right, our water reduction reaction. And well, we still want to at least kind of make sure that the electrons are balanced because we do need to get the correct N. And they did kind of help us with the 2 here. So although we don't need to multiply by the electrons, right, for the E cell. So that's kind of the difference. Okay, this is what we're looking for. So 2 waters. So again, we do need a scale that it is 2 electrons. Then correct direction, so negative 0.83 volts. And add those numbers. And so we should have 1.88 volts for our E cell potential. And so now can you take this number and get our delta G? So again, plugging it in. And so now we should be a little more cognizant of the electrons, if that makes sense. So again, right, you don't multiply up here, you just get your cell potential. And then down for our delta G, that's where we can take into account the number of electrons. So 2 again. So what do you get? Oops. Sorry, I didn't do that right. Let's try again. So I get this number for our Gibbs free energy. So let me know if you get the same thing. Somebody got a different answer in the chat. I'm double checking my own math. Because we should only have 2 electrons times 96,485 times 1.88. So I see somebody else got what I got, like negative. So we also got that in here. Okay, just checking. They're all on the same page. So negative 363 kilojoules. So again, just confirming that this process is spontaneous, which again, I think we all kind of predicted. All right, good. So now let's try our next one. So slightly different, but similar. And so now if we want to solve for our K, well, we have, again, this relationship. And again, it should be log here. So this is log base 10 using this number here. And so now let's go back to our problem. And so it wants us to, again, right, find our E cell first. So calculate that. And then this time, let's try to find K then. And I'll rewrite at least one form of the equation that I have. So the E cell equals 0.0592 volts over N, where again, N is the number of electrons. Yes, somebody's already jumped the gun that the book does use a slightly different form. So I'll bring that up in a second, but yes, it is confusing. So I have this slightly different form with log I have the book's version of the Nernst equation. I could try to pull it up too to compare. So your book, I'm just trying to show you what your book shows. I'll just call it book form. So if you're looking in your book and you're following along, the formula does appear slightly different. Again, the whole thing is plugging in this RT at 25 degree. And yes, like somebody pointed out, your book uses natural log of K. And so they have a slightly different V value there. So if you're using base 10, that's where I got this 0.0592 volts versus their 0.0257. It's because they're in a different base. So that's the only difference between those forms. And then obviously they did algebra to rearrange it like this way, but it's the same equation. So again, that's just natural log versus base 10 log. So good catch though that you were on that. Forgot I was muted. All right, so now add those two together. So now we have negative 0.34 volts. Sorry, repeating myself for online. And then now we can plug it in to our formula. I'm probably just going to use this form because to me it's a little easier. Again, it shouldn't matter if you plug it into this form. And then just keep in mind they use the term VE to signify number of electrons again. So same thing. So right, N is number of electrons or VE. So same. They're the same. just slightly different symbols. And so now let's plug this in. So negative 0.34 is equal to negative 0.0592 volts over N times our log of K. And again, my form, I'm using base 10. You're, again, welcome to use this one. Just make sure you're punching in natural log. And now N equals 2, so I got to plug that in. So now let me know what you all get as I finish. So then I get something of 11.49 is equal to my log of K. And then again, since I'm in base 10, yeah. Did I plug it in wrong? Oh, I must just have, that's a me error. So sorry. Let's get rid of that. So then it should be negative 11, which sounds better. And then 10 to the power, again, just watch what form of the equation you're using. And so then let's just rewrite this. So 10 to the power of negative 11.2.49. And so I have a K of about 3.24 times 10 to the negative 12, which again, right, that kind of makes sense. So we had our negative potential, so I would not expect our K, right, to favor our products very much. So that's in line with that. Good. Any questions on those? And so then the last part is just starting to kind of deal with some of these different concentrations. And so we're given this derivation for our Nernst equation. And so again, basically, this is giving us our deviation from kind of our standard cell, right? So we've been saying, okay, we're always 1 mole, standard conditions. But now we want to address, well, what if we're not at these standard conditions here? And then this is where my formula is wrong. So I think this is fine. It only got messed up because my form has natural log here, but that's a typo. It should be regular log. Again, otherwise you can refer to your book. Let me just paste it, because again, your book does have a similar but different form only because they're in natural log. Trying to find, yes. And so the degree symbol just means a standard cell potential. So it's saying, right, we take our E cell, basically what we've been calculating, except that's always standard cell, so meaning 1 molar, 25 degrees Celsius, same concentrations. And so now we're attempting to deal with different concentrations. Oh, that was a terrible copy from your book. But this is the book form. So again, it's the same. It's just they're in natural log. So if I can zoom in to get it slightly clearer. Well, your book has terrible resolution, apparently. Well, zooming in didn't help. All right, so again, same form. So I'll just say book form, but they're using natural log in the book as opposed to base 10 log from my notes here that I've pulled. So same formula, and then again they use different symbols for some reason for n. So your book uses this VE versus the N on this one, but again they're the same thing. So N equals our VE equals number of electrons in our process, and the electrons should be equal. All right, so that's where everything came from. So again, if you went back to this form, you could derive this number here, right? That's where this number comes from, the RT over NF. And so what we're trying to deal with is, again, this whole difference in concentrations. And so it brings up this interesting point, which I should have brought a demo for in retrospect. And so it's possible to get a spontaneous reaction when the oxidation and reduction reactions are the same, as long as the electrolyte concentrations are different. And so like we've kind of hinted at, and there's been some great questions kind of asked, it's like, well, you know, there could be some effect that we're not seeing because of, you know, kind of Le Chatelier's principle and the difference of electrolyte conditions. And again, that can kind of work to drive the cells as well. And so the difference in energy is due to the entropic difference in these solutions. And so the more concentrated solution, that seems backwards. Well, now I'm questioning that. But okay, basically there's an entropic difference. And so the electrons will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution. And so looking at what it's getting at, so now we have a comparison. And so we have made our little voltaic cell. And so looking at standard conditions, so this would be if we were trying to make a battery with copper and copper. And so, right, there's no movement of ions here. And then now when we have a difference in concentration, then our electrons flow from our side with our less concentrated solution to more. And so now let's kind of look at this. Like I said, I should have grabbed some solutions. I didn't think about it in time. Maybe I'll start off next week with this. All right, so we have a 0.01 molar solution, and then it's acting as our anode, again, from what it's saying, that it flows from our less concentrated to more concentrated. And so liberates electrons, makes sense, so then we get probably more ions in solution, right? So then more copper ions will be coming out versus them being plated on this side. So then our more concentrated, right, is plating out copper, so taking those ions out of solution. And so then we do get, right, these non-standard conditions, and it gives us, so 0.068 volts there. And so that's also what can happen, right? We don't, going back to the demo that I did now, like 2 weeks ago or so, right? That's why I didn't quite make it to 1.10 volts, because probably my concentrations were slightly off. And so that can also lead to variations. All right, so now let's calculate this and look at our concentrations. And so let's try to look and see if we can calculate this out. So let's kind of go through this together, because what we want to do is, again, plug in our equation here, our ln Q, or log of Q. And so let's go through that. And so first we just set up, right, our standard conditions. So, right, calculate, again, our E cell. And again, this circle reminding us that it's standard E cell, right? So same concentrations, assuming 1 molarity. And so, again, I'll be explicit with this. So, okay, we have copper, gives us copper 2+ and 2 electrons. And so let's just double check which way our sign goes. So that would be negative 0.34 volts. And then, right, we're trying to run our cell with the same thing. So copper 2+ plus 2 electrons gives us copper. So that's positive 0.34 volts. So, okay, we get back to our standard E cell potential of 0 volts, right? So again, that's what is shown here. So there's no concentration difference. And so now let's plug this in to either one of our equations. And so looking, so our E cell, and so this is actual E cell, right? So non-standard conditions, so now we don't have the little circle. And so that means we take our standard E cell minus, let's go, sorry, I was debating what form to use. Let's do 0.052, 0.0592 over 2 times my log, and again, I'm in base 10 of Q. All right, so now we have to define what our Q is for this one. And so we can, right, plug our concentrations in. So our final products. And so we want to compare, right, our copper 2+ concentrations. And so we're looking at now our difference in concentrations. So then it's going to be our log of Q is essentially our 0.01 molar over our other concentration, so over our 2 molar there. And so now I'm just plugging in values. And then again, don't forget your 2 to account for the 2 electron process. And so now I'm going to plug this in. So log of 0.01 over 2. Then times so question, do we have to use the F? So we've already kind of solved for that, right? So that's why we have this funky 0.0592. So if you were to go back, right, and plug it into this form, that's where the F comes in. But we've already calculated R times T over F for, again, 25 degrees Celsius. So that's why we don't need to worry about it. All right, plugging in, so times negative 0.0592 over 2. And so we get 0.068 volts for our potential there. And ta-da, right, that's what happened. And so that's telling us, right, our true E cell potential with, again, non-standard conditions there. All right, we're kind of running out of time. So kind of depending on how we're feeling. So we don't have like a quiz. I call it a practice quiz for fun. So it's just over like oxidation states and some other practice doing some redox reactions in acidic solution. So we could kind of work on that, or I don't know if people wanted to do, I have some more examples for some problems that are related to 25 if we'd rather just do 25 practice. Yeah. Let's see. I think it's because you want to get your equilibrium equation. It's just this one is. So I think you generally want to go anode over cathode. And again, just looking at the ions in solution, right, since your solids don't matter in that one. So yeah, it's always anode over cathode. So how are we feeling? Do we want to do quiz? Do we want to keep doing a few 25 problems? I feel like we should do more 25 problems. So yeah, maybe let's just go like 10 more minutes of lecture. Yeah, and we could do, because people want to do another standard one too. So let's do that. Let's see. So let's look at this cell. And so let me write it out. So we're looking at this cell. So basically we want to figure out what is our E cell concentration. And again, I've dropped the 0 because it's non-standard conditions. And what if I give it to you like this? So we have this situation here. And so what if I give you this? Can you calculate the E cell? So I'll give everybody a few minutes to try it out. So this is a good one to try for a few reasons. So again, it's not only non-standard, but we got to watch those electrons in this process. So yeah, it looks like good progress so far. Some questions of like, do we need to consider reactivity? But that's kind of what's implied with these redox potentials. So again, like if you get a negative one, that kind of implies, well, that's not, great, or, right? So that's kind of like giving us a hint to the reactivity, which again kind of goes back to like the power of the CV stuff that I was saying. And then I'll start. We might have different numbers too, at least slightly different. So I have chromium, gives us chromium 3 plus. Where's chromium? So I have that as positive 0.73. And I'm assuming the negative 0.02 volts in the chat is going to be for the standard E cell potential. And then zinc. So what do we get for zinc? So negative 0.76. Yeah. Because of the direction that it's going in, right? So zinc, it's how it's written here is the form that it's going in, right? So if you go back to your cell, so this is your anode, right? This is your cathode. So then this is going to be going zinc 2 plus 2 electrons to give you zinc. So then that's the negative 0.76. And I get -0.03 volts, but again, there could be some slight discrepancies, so I'm assuming that's why probably someone in the chat got .02 volts. I'm assuming. Again, it shouldn't matter too much, right? Plus or minus a few. And so again, this is our standard E cell. And so now we have to plug that in. So I'm just rewriting my formula for a second. So minus 0.0592 volts over N times my log of Q. And so what should we put for N though? 6, good. So that was the second tricky part of this is, okay, well now we do have to balance our electrons. And yeah, we have a 3 and a 2, so lowest common multiple. So good, 6. You guys are on the ball. So now just plugging in these values. And again, it's anode over cathode. Oh, and we should take into account our equivalence, right? So that's why. So I cubed. So this is times 2. So you square your top one and then cube the bottom. So again, more tricky things with this problem to account for our equivalence. So again, this is a good example to run through for all these like little places to make errors. And let's emphasize this. So correct for equivalence and our expression there. Okay, now I think I'm finally ready to punch it into the calculator. So I get a negative number still. I mean, there could be, again, small discrepancies depending on what voltage we use. So I don't know what other people got. So it sounds like people got the same. So negative 4 times 10, the negative 4 volts here. But I'm going to say, right, could be slight discrepancies. And I'm just kind of thinking if we were trying to cheat, that negative 2 volts kind of works out a little better to give us a positive potential. But maybe we'd want to experimentally double check this one as well. But again, just kind of going through the math, that's how you do the process, right? Again, there could be small discrepancies in your voltage. So it's okay if you got a positive voltage. That's kind of what I was expecting, but didn't math out that way. Yeah, so I was kind of thinking of that. Now YouTube has crashed on me, I think. All right, let's try one more kind of representative problem from the chapter, and then that'll probably be a good place to stop. And again, I don't know what's going on with YouTube now. So let's say, how long will a 1.17 amp current need to pass through an electrolytic cell containing copper 2 plus aqueous to plate out 5 grams of copper. So you might have to go back to like the first few bits of this section. Hoping the YouTube will come back. Okay. Not sure the stream is going. Oh, somebody says it's good. I can't tell. It's still giving me a YouTube error even though my stream health is registering good. All right, let's go over this one. And so again, we have to think back to what an amp is. And then, good. So people are recognizing, right, we have a 2 plus charge. So that means, right, we're going to need 2 equivalents of electrons. And I'm kind of thinking about Faraday's constant. Again, right, we're going to need that. So 96,485, right, coulombs per moles of electrons. Okay, that's good that you guys recognize it's 2. Then, yeah, if you want to grab the fun quiz just for practice, I can post answers or we can go over it on Tuesday. All right, and then don't forget what an amp is either, right? So that's telling us, so 1.17 coulombs per second. And so I think things will come out now of our formula. So what do we want to calculate first, right? They gave us yeah, moles, right? So we need moles of copper, and then we'll multiply it by 2, right, to give us moles of electrons. So that's essentially where we're going. So 5 grams divided by, oh, thank you, 63.55. And then I'm just setting up my dimensional analysis. And then, okay, that gives us moles of copper. But then, like you guys caught on, well, it's copper 2 plus, so that's 2 electrons, right, for every 1 mole of copper. And then now we can plug in our Faraday's constant, which I put a little bit too close to my work here. Let's try to move this down. Oh. There we go. So now there's our Faraday's constant. So that's how many coulombs, right, we need. So now that's coulombs. And so to give us time, right, for our amps, so now we need to divide it by how much current we're going through to give us seconds. So that's why I like rewriting this as such. So now we can see, okay, that means I want to put 1.17 coulombs on bottom. I'm going to get seconds out on top. And so now we just have to plug it all in across. So moles of copper again, times 2 for our electrons, then times 96,485, divided by our current. And so now I get that many seconds. So 12,976. And I'll put this into probably hours or something. So divided by 60, so that's minutes, divided by 60. So about 3.6 hours there. So I think those are all kind of like the main representative types of questions that we'll see. So you'll probably definitely see this on the exam in some way, shape, or form, probably very similar, just different amounts and different amps. And then going back, I think these will be like the hardest in quote questions, but I can't remember what's on your exam at the moment if I do anything. This would be like as tricky as it gets, right? Trying to account for difference in moles of electrons and calculating for that. But otherwise, I think most of it should be fairly straightforward. Again, this is our good kind of cheat sheet right for the end, and then just keep in mind the two different forms of the equation, right? Your book uses natural log, my notes use base 10. They're the same. All right, I'll probably stop here for today. That's a lot of good 25 review. And then, like I said, if you want to do the fun quiz, you know, it's here. It's just for practice. In case people wanted more oxidation state practice. And then if you want it emailed to you, I'm happy to email it, or maybe I'll just post it on Blackboard, but I can also email it if anybody just wants it like emailed directly. But yeah, I'll probably post it on Blackboard, and then I don't know if people want to like go over it on Tuesday or if I should just post answers for that. You can kind of let me know. But I'll probably stop yammering, and then y'all can use this time to either just like catch up on things. So yeah, play catch up. And then, oh, otherwise I'll see y'all on Tuesday for the field trip. So again, wear warm clothes, drive safely, all those good things. I'll see you then. Yeah, carpool, get your last minute carpools. I'll stick around on stream in case there are questions.